Let's go through the entire grade 12 calculus course in under an hour. So I'm going to break this video into 3 parts. You can read those parts here. And note, I'm going to be going through the examples relatively quickly because this is meant as a review of everything you've learned, or maybe a preview of what you're going to learn when you take the calculus course. If you want more detailed explanations of each of the topics I'm going to do, you can visit jensenmath.ca, go to the calculus section, and you can also go to my YouTube channel, find the calculus playlist, and you can get videos in more detail about each of the topics there as well. So in this video, we're going to start with part 1. So every calculus course starts by talking about limits and Newton's quotient. And Newton's quotient is a way of finding the equation of the derivative of a function. And what's the equation of a derivative? Well, a derivative is a function that we denote with, f prime of x, that finds you the instantaneous rate of change of f at x at any point we want. Let me tell you graphically what I'm talking about. Well, let's say we wanted the average rate of change between 2 points on a function. That's represented with the secant line, and we could find the average rate of change just by doing change in y over change in x between those 2 points. But if I want the instantaneous rate of change, like let's say at this blue point here, what if I wanted to know the instantaneous rate of change at that point? Well, that's represented by the slope of the tangent line to the function at that point. But how do we find the slope of a line where we only know 1 point on the line? Well, if we look at the slope of this purple line, which I have calculated here, negative 6.15, and compare that to the slope of the tangent line, which I have calculated here as negative 3, watch what happens when I slide this point closer to this blue point here. Watch what happens to the slope of the secants compared to the slope of the tangent. As I move it closer, the slopes of the secant are getting closer and closer and closer to matching the slope of the tangent. Okay, so you say, well, why not just move the points right on top of each other? Because if I do that, notice my change in y over change in x becomes 0 over 0, which is undefined. So we have to look at the trend, we have to look at the limit of what's happening to these secant slopes as the change in x is approaching 0, as the points are moving infinitely close. And that's what Newton quotient tells you to do. It says find the slope of the secants where the change in x of the secant points is approaching 0. And we write that like this. Find the limit as the change in x, which we call h, approaches 0, of the rate of change between f at x plus h minus f at x, right? That's just our change in y values, all over our change in x values, which we're calling h. So this is Newton's quotient. It finds what the secant slopes are approaching as the change in x approaches 0. Okay, so let's use the Newton quotient for this negative 3x squared plus 1 function. So this equals the limit as h goes to 0 of f at x plus h. So replace that x with x plus h, so negative 3x plus h squared plus 1. And then I have to subtract the f at x function. So subtract negative 3x squared plus 1. And that is all over our change in x, which we represent with h. And we want that change in x to approach 0. We can't let it be 0 because then we'd have 0 over 0. So limit as h goes to 0. Let's simplify the numerator. Negative 3 and then x plus h all squared is x squared plus 2xh plus h squared. Plus 1, distribute the minus, plus 3x squared minus 1. And this is all over h. And then I'll very quickly distribute my negative 3 plus 1 plus 3x squared minus 1 all over h. And then if we've done this properly, you should notice that every term that doesn't contain an h should cancel out. So I have a plus 1 and a minus 1, that's 0, and I have a negative 3x squared plus 3x squared, that's also 0. So there's 2 terms left in the numerator, and notice they both have an h. So I can common factor an h out from both of them and get negative 6x minus 3h. And that's all being divided by h. If I plugged 0 into this, I would get 0 over 0, which is undefined, but we're interested in the limit as h approaches 0. So I'm able to cancel those out, right? H over h is 1. And what I'm left with is negative 6x minus 3h. And that I can actually plug 0 into and get a value for. So negative 6x minus 3 times 0 equals negative 6x. So that's the equation of the derivative. F prime of x equals negative 6x. This function would tell me the instantaneous rate of change of f at x at any point I want. Like if we look back at what we talked about earlier, looking at the slope of the tangent at a half, I could figure it out by doing f prime at a half equals negative 6 times a half, and figure out the instantaneous rate of change, the slope of the tangent, at an x value of a half on the original function is negative 3. So notice looking back at this original function, the slope of the tangent at that point, I have it being calculated right here, is -3, and we calculated that using the equation of the derivative. So after you do Newton quotient, you learn a whole bunch of derivative rules that we can use to calculate derivatives without having to go through Newton's quotient each time. And if you follow this link I'll post in the description, you'll see that I have all the derivative rules listed out for you. Things such as product rule, quotient rule, chain rule, a bunch of trig and exponential derivative rules, and so on. So you can follow that link in the description, but we're going to do a bunch of practice examples using those rules now. So let's find the equation of the derivative of a bunch of functions, and they'll start off from easy to more complex. So this function here, y equals 4, well 4 is a constant, and the derivative of any constant is 0. Right? Constants don't change. This is the rate of change. So y prime equals 0. How about this one? We need the power rule. The exponent on this power of x is 1. So what we do is we multiply the exponent by the coefficient when we're getting the derivative. So 1 times 3 is 3. You keep the base of the power x and you reduce the exponent by 1. So what we have is y prime equals 3 times 1. Right? Anything to the 0 is 1, so 3 times 1 is 3. Part C. So this time I'm doing the derivative of a sum of a few terms. And what we do when we do that is we just differentiate each of the terms independently. So if I want the derivative of this function, I just have to differentiate this term plus the derivative of this term minus the derivative of this term. Well, what's the derivative of 5x cubed? We'll multiply the exponent by the coefficient and get 15. Keep the base of the power and reduce this exponent by 1, so 15x squared. Plus the derivative of 3x to the 1 is just 3x to the 0, which is just 3, minus the derivative of a constant is 0, so minus 0, which I don't have to write. So there's the equation of the derivative. How about part D? It would probably help if I rewrote this one by bringing this power up to the numerator. That way I can just use power rule instead of having to do quotient rule. So it becomes 3x to the negative 4. And now I can use power rule by multiplying the exponent by the coefficient, getting -12, and reducing the exponent by 1 becomes -5. And any final answer should not have a negative exponent in it. So bring that power back to the denominator, it changes the sign of the exponent, makes it x to the positive 5. Okay, that's 4 derivatives done. Let's try a fifth one where we need product rule. Right, we have a product of two functions here, 2x plus 3 multiplied by 5x minus 1. And the product rule tells us that we do the derivative of the first function, so the derivative of 2x plus 3 is 2. Multiply that by the second function, plus we do the derivative of the second function, which is 5, times the first function. And then it's just a matter of simplifying it, right? So product rule, derivative of first times second, plus derivative of second times first. That's what I have here. We'll just expand and collect. So distribute the 2, distribute the 5. I get 10x minus 2, plus 10x, plus 15. F prime of x equals, collect my like terms, 20x, plus 13. Part F. This time I'm going to need chain rule. Right now I have a power of a function. So for chain rule, what I do is I differentiate the outside function with respect to the inside function. So that means bring the exponent down, so 2, keep the base the same, and reduce its exponent by 1. And now that needs to be multiplied by the derivative of the inside function. So the derivative of the base of the power is 3, so multiply it by 3. And then I can multiply the factor of 2 and 3 together and get 6. So 6 times 3x minus 2. And I guess I could distribute that. I could get 18x minus 12, but I'm going to leave it in factored form. Let's try this one here where I need to now use quotient rule. So for quotient rule, the rule for quotient rule, when we do the derivative of a quotient of two functions, we do derivative of top times bottom minus derivative of bottom times top all over the bottom squared. So derivative of top is 3 times the bottom function minus the derivative of the bottom function, make sure that goes in brackets, times the top function all over the denominator squared. So all over the bottom function squared. And then we just have to simplify this. So I would expand the numerator and collect any like terms. So I've got 3x squared plus 6x minus 12. And then I need to subtract this product. So this product would be 6x squared, so I have to subtract 6x squared. And then 6x, so I have to subtract 6x as well. And the denominator stays the same. And collect my like terms in the numerator. And I would have negative 3x squared the 6x's cancel, and then minus 12. And once again, I could leave it in this format, or I could common factor out a negative 3 from the numerator and get x squared plus 4 and leave the denominator as it is. So last derivative example. This time let's use Leibniz notation. Instead of using y prime, I'll use dy over dx. It means the same thing. It means the difference in y with respect to the difference in x equals derivative of top, 3, times the bottom, x squared minus 2 squared, minus the derivative of the bottom function, which I'm actually going to need chain rule for, right? So bring the exponent down, leave the base the same, reduce the exponent by 1, and that needs to be multiplied by the derivative of the inside function. The derivative of x squared minus 2 is 2x. And so that's the derivative of the denominator, but that then has to be multiplied by the function in the numerator, so by 3x. And that gets put all over the denominator squared. So all over x squared minus 2 squared squared. Now let's simplify this up. So dy over dx equals, and I'm going to leave this 3x squared minus 2 squared, but then over here I've got a factor of 2, 2x, and 3x. I can combine those and get 12x squared. And denominator, I have x squared minus 2 squared squared, so the power of a power, I multiply those exponents together, so it becomes x squared minus 2 to the 4. Now in the numerator, notice that I have two terms. I've got a term here and a term here. Notice what's the same with those two terms. They both have a factor of x squared minus 2, and they both have a factor of 3 that I could take out as well. So I'm going to common factor the numerator. So I'm going to common factor out a 3 and an x squared minus 2 from both of the terms. And when I divide both of those terms by what I divided out, I would have x squared minus 2 from the first term minus 3 divided by 12 is 4. The x squared is still there, but this x squared minus 2 has been divided out. And this is all over the denominator. And something nice happens here as well. This x squared minus 2 cancels out with one of these factors, so we're left with 3 of them in the denominator. So my final line here, I've got 3, and then inside here I've got x squared minus 4x squared, that's negative 3x squared, and that minus 2 is still there, all over x squared minus 4 cubed. So there's my final answer. Let's move on to some applications of derivatives. So determine the equation of the tangent to the curve. So I want the equation of the tangent to this curve at the point where x equals 1. Well, what does that mean? Let me make sure you understand what the question is asking. So let me go to this Desmos link here. So I've got the function graphed. So here's the function, this function here, f of x. We want the equation of the tangent line at x equals 1. So I've got Desmos graphing that tangent line for us. We want the equation of that tangent line at this point right here. Well, if we want the equation of the line, it needs to be in the form y equals mx plus b. Well, we can get the slope of the tangent line from the derivative. So we'll find the derivative to get the slope of the tangent line, right? That's the purpose of the derivative, to tell us the instantaneous rate of change. And then to write the equation in the form y equals mx plus b, we not only need the slope, but we need the y-intercept. So you'll have to plug in the slope and a point xy to be able to solve for b. And the point xy, well, the only point we could use is the point the tangent line shares with the function, and that'll be at an x value of 1. So we can plug 1 into the original function and get a point xy, and then use all that information to solve for the y-intercept. So let's actually go ahead and do this question. Let's start by finding the slope of the tangent line. So the derivative tells us the slope of the tangent at any point we want, so we're going to need the equation of the derivative. And I'm going to need product rule for that. So derivative of the first function is 4x times the second function plus derivative of the second function, 2 times x plus 1, times derivative of the inside based on chain rule, which is actually just 1, times the second function. So that's the derivative. It's not simplified, but that is the derivative. I technically don't have to simplify it for this question because all I'm interested in is the slope when x is 1, so I just have to plug 1 into this equation. I'll simplify it just for fun though. So if we simplify this up, I could common factor a 2 and an x plus 1 from both of my terms, right? I have a term here and a term here. I'm going to take out a 2 and an x plus 1 from both of the terms, and that leaves me with 2x times x plus 1 for the first term, plus all I have left is this 2x squared minus 3 from the second term. and I'll simplify this. So that's the equation of the derivative. I can use that to find the slope of the tangent at any point we want, and we want the slope of the tangent when x is 1. So let's plug in 1 to this. I'll get 2 times 2 times 3. So f prime at 1 equals 12. That tells me the slope of the tangent when x is 1 is 12. So I have the slope. Now keep in mind we want the equation of the tangent line in the form y equals mx plus b. We now have m. M is 12. We're interested in solving for b, so I need to figure out what I can plug in for x and y. Well, x we know is 1, but what's the y value that goes with that on the original function? What we have to do is then plug 1 into the original function for x. So we're going to now solve for a point that is on the original function and on the tangent line by plugging in 1 for x into the original function. So f at 1 of this original function here. So that would give me negative 1 times 4, so negative 4. So f at 1 is negative 4. So the point on the tangent line, which is also on the original function, is the point 1, negative 4. There's our x, y. So over here, when I'm finding the equation of the tangent, now I can just plug in negative 4 for y, solve for b, I get negative 16, which means the equation of the tangent is y equals 12x minus 16. And let's make sure that matches up with what we had on Desmos here. Yep, slope of 12, there's the slope, and y-intercept of negative 16, so there's the tangent line. Next example, for this function, determine the points where the tangent line is horizontal. So let me just show you what we're talking about here. So I have this function graphed, and we're interested in when is the tangent line horizontal? Well, notice the tangent line is horizontal in a couple spots, around here, and then also here at 1. And what's the value of the derivative of each of those points? Well, I've got it telling me here the value of the derivative is actually 0, right? The slope of a horizontal line is 0. So I'm looking for when is the equation of the derivative equal to 0, and then that will tell me when the tangent line is horizontal. So what I have to do is find the equation of the derivative, which I can just use the power rule for with each of those terms and get 3x squared minus 2x minus 1. And now I'm interested in when will I have a horizontal tangent, so when is the instantaneous rate of change 0? So when is the derivative 0? So now I just have to solve this equation. And this is a quadratic that I could factor, right? I'm looking for a product of negative 3 and a sum of negative 2. And the numbers that work are negative 3 and 1, so I split the middle term, and then I factor by grouping. Common factor a 3x from the first two terms, and common factor a 1 from the last two terms, and I get a common binomial, which I could factor out, and I get x minus 1 times 3x plus 1. So I get two answers for x. I get 1 and negative a third. Those are the two values that make the derivative be 0. So those are the two places on the original function where I would have a horizontal tangent, right? At 1, you see it here, and then also at, we figured out negative a third. And notice there's also a horizontal tangent, right? The equation of the derivative is equal to 0 there as well. Oh, and the question says find the points. So it actually wants, we need the y coordinates as well. So we know the x coordinates, we need the y coordinates. So we'll need to figure out what is the value of f at 1 and what is f at negative a third. So 32 over 27 and 0. So the 2 points are 1, 0 and negative a third, 32 over 27. Those 2 points on the original have a horizontal tangent. Example 4, an object moves in a straight line and its position s in meters after t seconds is given by this equation. Determine the velocity and acceleration when time is 5. Well, if we have a position function, we can calculate the velocity of a function by just finding the equation of the derivative of its displacement function. So s prime at t equals, differentiate this, 0, negative 7, minus 2t. And let's find the velocity at 5. So all we have to do is negative 7 minus 2 times 5, and we get negative 17 meters per second. Here's part B. To find acceleration, I just have to find the rate of change of velocity. So find the derivative of the velocity equation, that would just be negative 2. So the acceleration is actually always negative 2 meters per second squared. So acceleration at 5 is negative 2 meters per second squared. Example 5. Here's a business application question. A store sells 250 pairs of brand X running shoes each month when priced at $100 per pair. It has been determined that for every $5 decrease in price, an additional 20 pairs will be sold. We want to find the demand or price function, find a revenue function, and then calculate revenue and marginal revenue at different values of x. So for this question, part A, determine the demand or price function. In this application context, we always want to write the price function in terms of numbers sold. So let's look at what variables we have. So we have a price. The price started off at 100, but they're thinking about decreasing it a certain number of times. So it started off at 100, but they're thinking about decreasing it by 5 a certain number of times. And that number of price decreases, I'll call that n. And numbers sold, they sold 250, but that's going to go up by 20 every time they decrease the price. So 250 plus 20 every time they decrease the price. So plus 20n. But we want to write the price function in terms of x. Right now I have price written in terms of n, written in terms of number of price decreases. So what I'm going to have to do is replace this n with a function of x. So I'm going to take this equation here, x equals 250 plus 20n, and I'm going to rearrange it to isolate for n. So I've got x minus 250 divided by 20 equals n. And what I can do is I can take this expression for n and replace that n in the equation with it. And then I have the price function written in terms of only x. So price equals 100 minus 5 times x minus 250 over 20. So there's a price function written in terms of numbers sold. And that's what we do in the business application. So P at x, I'll simplify this a little bit. P at x equals 100 minus 5 times, now the x and the 250 are both being divided by 20, and then I'll distribute and simplify. P at x equals, and then I can collect my like terms. P at x equals, that's the price function. Part B says find the revenue function. Well, a revenue function is equal to the price times the number sold. It's always equal to x times P at x. So in this case, revenue would be equal to x times negative 0.25x plus 162.5. Distribute the x. There's my revenue function. Part C asks me to calculate the revenue at a couple different values. And I'll just plug that into my calculator quickly. So revenue at 250 and 290. So if I want to calculate the revenue at those two amounts of numbers sold, I've got the equation typed here already. Let's get revenue at 250 and the revenue at 290. So the revenue is 25,000 and 26,100. Part D asks me to calculate marginal revenue. When you see the word marginal, make sure you understand that means the rate of change of the revenue, which we can use the derivative for. So to determine the marginal revenue at 290, so I need to find the value of the derivative at 290. So D, I need to first figure out what's r prime of x, and I'll find the derivative of the revenue function here, so it'll be negative 0.5x plus 162.5, and I want r prime at 290. So I'll go back to my calculator, and I'll evaluate r prime at 290, and it's 17.5. So that's actually the rate of change of the revenue at that number sold. So it's 17.5, so that means the revenue is going up by $17.5 per unit sold. That's what the revenue is changing by at that number sold. It's changing by $17.50 per unit sold. Example 6, given the graph of f at x, sketch a possible graph of f prime of x. So keep in mind the derivative tells you the tangent slope to any point on this original function. So the y value of the derivative when x is negative 2 would probably be 0 because it looks like there's a horizontal tangent there. So I can plot that point. There's also a horizontal tangent there and here. So at those x values, the derivative would be 0. Now I just have to figure out would the derivative have negative or positive values in each of the intervals in between here. So before negative 2, the derivative is going to be negative. I know that because the original function would have negative tangent slopes for any x value before negative 2. So it's going to have, the derivative is going to have negative y values. How about between negative 2 and 0? The function is increasing, which means the derivative is going to have positive y values. Between 0 and about 4.5, the function is decreasing, so it's going to have negative y values. And then after about 4.5, the function switches to increasing, which means it has positive tangent slopes, which means the derivative has positive y values. Example 7. Given the graph of f prime of x, let's sketch a possible, it says state the intervals of increase and decrease for the function, then sketch a possible graph of f at x. Now, the y values of the derivative are going to tell me whether the function is increasing or decreasing. So for f at x, it's increasing whenever the derivative is positive. So it's increasing when x is greater than 1. And it's decreasing when x is less than -2, right, because the derivative is negative there, and also when x is between -2 and 1. At -2, it's not increasing or decreasing because the value of the derivative is 0, and at 1, it's not increasing or decreasing because the value of the derivative is 0. So I need to sketch a function that satisfies this criteria. Decreasing before -2, still decreasing after -2 until 1, and then at 1, it switches from decreasing to increasing. So at 1, it's going to switch from a decreasing function to an increasing function. So I'm going to use green again here. So I know that there's going to be a minimum point at an x value of 1. I don't know where that min point's going to be, but I know there's going to be a min point at an x value of 1 somewhere. And I know at -2, there's a horizontal tangent because the derivative is 0. So somewhere at -2, there's a horizontal tangent. I'm just going to plot a point here. I don't know how high or low that point is. So before that point, the function is decreasing. At the point, there's a horizontal tangent. And then after the point, it continues to decrease. And it continues decreasing all the way until we get to an x value of 1, at which point it switches to increasing. So here's what the function looks like. Decreasing, 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 decreasing very slowly. And then at this point right here, there'd be a horizontal tangent, right, indicated by the y value of 0 for the derivative. Then it continues to decrease until an x value of 1, right, because the derivative's y values are negative in that interval. And then it switches to increasing after because the derivative's y values are positive after an x value of 1. So that's it for part 1. Make sure you watch part 2 where we're going to talk about curve sketching and some optimization questions.